mass spring system. So you recall what is going on. So if we have external force, when external force equals to force, combined force, so E squared y dt squared plus damping force. And damping force is proportional to velocity, y dt, plus stiffness of a spring. I think we used K times Y. Right. So if you like, F external inverse equals to inertia times acceleration plus damping times dy dt plus stiffness times y. Right. I want to figure out what is going on with this one again. So our first example will be, we assume that there is no external force, and we assume that damping also 0. So we assume that the damping is negligible, close to 0. Okay. So in this case, we're going to get 0 equals m, second derivative plus ky. We know how to solve it. So we set our auxiliary equation, mr squared plus k, mr squared equals to negative k, r squared equals to negative k over m. So r equals plus or minus square root of k over m times I. Okay. So our solution is going to be y equals c1, c2. There is no real part here, so with e to the 0, which is 1, cosine square root of k over m t plus sine square root of k over m t. And I'm going to be using notation square root of k over m, and I'm going to call it omega. So our solution is going to look like y equals c1 cosine omega t plus c2 sine omega t. We know how it goes. Good. So that part hopefully is straightforward. Now a little bit less straightforward part, a little bit less obvious part is the following. Here we start to sketching that solution for different C1, C2, and different W's. If we sketch the graph, it's going to look something like this. Right? And if you carefully look at that, that is sine curve. Right? That's exactly what you expect. If there is no damping, there's mass springs will be moving back and forth, back and forth, back and forth, back and forth, you know? If there is no damping, so that should be sine curve. So what we want to do is, with our solution, we want to rewrite it in terms of a sine curve. So let's try. So we're going to rewrite our solution in terms of sine curve. So we're going to write down C1 cosine of Wt plus C2 sine of Wt equals to sine. I guess I should have constant here, and I will probably have the same W omega t plus sine angle here. So that's what I will try to do. if you remember that sine of alpha plus beta, sine of sum equals to sine alpha cosine beta plus sine beta cosine alpha. Remember that formula? If you recall that formula, that's the one which you're going to be using. So we're going to rewrite a sine omega t plus phi as a sine of omega t cosine of beta plus, why am I using beta phi, plus a sine of phi cosine of omega t. And that should be equal to C1 cosine of omega t plus C2 sine of omega t. Now, if we try to match them, C1 cosine of WT here and C2 of sine of WT here. So A cosine of phi equals to C2 and A sine phi equal to C1. Yeah, thank you. And then if I try to solve a triangle, I can find that A equals to the square root of C1 squared plus C2 squared, and tangent phi equals to C1 divided by C2. So I should be able to write down my solution now in the form y equals to A sine of omega t plus phi. And now I can do different interpretation of what is written here. If I look at the solution, then phi is a shift. I can definitely figure out what the period. Period is going to be 2 pi divided by omega. I can see what will be the frequency. It's often going to be called natural period and natural frequency because that's what is a property of a spring. That's what is going to be happening to the spring without external force and without damping. Right? That's what property of a spring. That's natural period, and that's why it's natural frequency. So frequency is basically you flip your period, right? So how many rotations do you happen in 1 second? Omega divided by 2. And if you like, you also can call W angular velocity. Angular velocity. And if you like, omega equal to square root of k over m. Right, so let's do an example. So we have a mass spring system, right? Okay. And we assume the equilibrium position here. Here, we have some mass at the end, right? Some mass at the end. So what is happening is our mass and spring shifted a little bit to the left. So let's pick a number. And then it always has some initial velocity. Which way do you want to go, to the left or to the right direction? So initial velocity, V now equals, and let's pick a number. Okay. Let's pick something for mass. And let's pick something for the stiffness of that spring. Again. Okay, so we Okay. So we got all that information. Now let's see. Right. An equation for the position of the spring. So we have our equation 0 equals 3 dy dt squared plus 4 y. We can easily solve it regular way. Okay. 2 over root 3. Okay. 2 over root 3. Now we're going to rewrite it in, I guess before we do that, let's see. Let's find C1 and let's find C2. So to find C1 and C2, we need to look at the initial position and initial velocity. So when I'm looking here, I will assume that my positive direction is, that's positive. Okay. If I assume that positive direction is to the right, then y of 0 equals to -5, and y prime of 0 equals to 2. Because my displacement is to the left, left is negative direction, so y of 0 equals to -5. And because my initial velocity y prime of 0 equals to 2, I have initial velocity positive 2. So y of 0 equals to -5, y prime of 0 equals to 2. So we're going to get -5 equals sine of 0 is 0, sine of 0 is 1, so C1. C1 equals to -5. And find what y prime is. 2 over square root of 3, C1 sine of 2 over square root of 3t plus 2 over square root of 3 C2 cosine of 2 over square root of 3t. And I guess it should be minus somewhere here, right? It's not going to affect my answer because I know that sine part will make it disappear because sine of 0 is 0. So y prime of 0 equals to 2 implies 2 equals to 2 over root 3 C2. So C2 from here equals root of 3. So finally we have our answer, -5 sine of square root of 2. 2 divided by square root of 3t plus root of 3 sine of 2 root of 3. Okay, that's how we will be given answer in previous parts, like we were doing before. Y equals a sine wt plus phi form. Let's figure out what a is. A equals to square root of 25 plus 3, so square root of 28. If you like 2 square root of 7, that's better. Then tangent phi equals to C1 divided by C2. So -5 divided by root of 3. So phi from here equals to tangent inverse of -5 over root of 3. So if you like, calculate that expression, or if you don't like, just keep your answer the way it is. 2 square root of 7 sine 2 over square root of 3 t plus tangent inverse of negative 5 root of 3. So something like that. Okay. And now if we continue example, and say we have a question when the spring pass through the equilibrium position first time. So if you continue the same example, so basically what we need to know to answer is when y equals to 0. So when y equals to 0, we can address it from this form of our answer. So that is when sine equals to 0. Sine equals to 0 when its argument equals to 0, or if that's not, if we're not going to be happy with that, that is or equals to pi. Depends on which way we're going to go. So for this one, I guess we'll need to approximate what is tangent inverse of negative 5 over square root of 3 is. So 5,292 sine 0.155 t plus 2 minus 1.237. Okay. Like that. Now we set argument equals to 0. We're going to get t equals to 1.237 divided by 0.155, which is approximately in 1.07, depending on the units, second or whatever minutes.